Okay, let's write down some examples of ideals. Pretty much the only ones that I wrote down explicitly are these principal ideals, things like 3z, all multiples of 3. And in Z, these are the only kind of ideals after all. So I want to write down some more examples like this. Of course, you might say that we have all these operations on ideals. So if you give me some, I can make more by applying those operations. Yes. But this is just to have something explicit in mind. So we'll start with the ones that we saw. Ideals in Z are the subset 0, that's always an ideal, that's 0, all multiples of 0, Z itself, which is all multiples of 1, and then 2Z, 3Z, 4Z, etc. Okay. A priori, you could write down other things like the smallest ideal generated by 24, 36, and 54, but that turns out to be, again, just all multiples of 6. Remember, this was an exercise. Okay. Let F be a field, then the ideals in Fx, the one variable polynomial ring with coefficients in F, are of the form. So every ideal in the single variable polynomial ring over a field are again principal, where F is some polynomial. By the way, we proved this theorem for Z. I forgot to mention anything about the polynomial ring case. It's exactly the similar proof. We started with an ideal in Z, and we proved that it's all multiples of a single number. How did we find this number? This number was the smallest positive number in I. Similarly, you start with an ideal in polynomial ring. You want to show that this is all multiples of a single polynomial. How do you find that polynomial? You take this to be size corresponds to degree here, right? So you take Fx to be the smallest degree non-zero polynomial in I. And then pretty much the same proof goes through. You do division with remainders and exactly the same argument. Okay. So this much we know. So to see some other kind of example, you have to go to at least two variable polynomial ring. You can show, for example, the ideal generated by x and y in the two variable polynomial ring is not principal. So all these are exercises, if you will. So what is the ideal x comma y? These are all polynomials that, two variable polynomials that look like x times a two variable polynomial plus y times a two variable polynomial, where f, g are in the two variable polynomial ring, right? So there's a better way of describing this particular one, I suppose. If it's x times something plus y times something, all that it means is that you can get anything but things that have non-zero constant term. So this is same as all fxy in Rxy with 0 constant term. Meaning a two-variable polynomial in general can be written like this, right? a1 comma 0x plus a0 comma 1y plus a1 comma 1 xy plus a2 comma 0 x square plus a0 comma 2 y square, etc. So this two subscript thing is a good way of subscripting them just by the degrees. But as long as the constant term is 0, so there is no constant term, then you can you're going to have either a x and a y, or a y in every term. So you can take the x terms and say, oops, and factor out a x, and from the rest you can factor out a y. Yeah. So all such things would be in this ideal, and the ideal consists of all such things. There's another way of describing this set. This is all f in the two-variable polynomial ring whose value at 0, 0 is 0. Right. Value of a polynomial, two-variable polynomial at 0, 0 is exactly the constant term. This, you can check, is not a principal ideal, so it's a different kind. Okay. This one is sort of a master example. Let A be a set. So it's a very general kind of example, whereas these were very specific. And let R be a commutative ring with 1. And let S be a subring of this function ring, functions from A to R. Remember, fun AR means the set of all functions from A to R. Fun AR means the set of all functions from A to R, and this forms a ring under pointwise addition and multiplication of functions. So S is some subring of this. So it's a collection of functions from A to R that is closed under addition and multiplication. That's what S is. Remember, we have this homomorphism we defined when we talked about homomorphisms. Called E sub A, E for evaluation, from S to R, defined by evaluation at A of a function is the value of the function at A. That's why it's called evaluation homomorphism. So the input is a function from A to R, and the output is f of A. So here A is some fixed element of R. So let's fix A in R. For a fixed element of the ring, we can evaluate at that element, and that gives me a homomorphism from this ring of functions to the ring R. What is the kernel of this homomorphism? The kernel of this homomorphism is all the functions in S such that E sub AF is 0, meaning f of a is 0. So these are all the functions that vanish at that point. Okay, and that is a interesting ideal. We'll write that IA, the ideal of functions vanishing at A. Okay. So this is a two-sided ideal in S. Because kernels of any homomorphism, remember, are two-sided ideals. More generally, actually, given any subset B of your A, you can consider I of B, which means all the functions in S such that they vanish not just at a point but all elements of B for all B in capital B. So these are the functions that vanish on this subset B. And you can check that this is also a two-sided ideal. In S. And these are very important kinds of ideals. I mean, it's a very straightforward construction. Just as I told you that these homomorphisms are very important, these ideals are also very important. And one way to check that this is ideal is just to note that IB is really just the intersection of all these IAs, where A varies over the set B. If you have to vanish, if your function has to vanish on B, it just has to vanish at every point of B. So I sub A is the set of functions that vanish at A. Okay, so, and each IA is an ideal, so the intersection of them is also an ideal, because the intersection of a bunch of ideals is again an ideal. Okay. Maybe I'll give, my notes has a few more. Maybe I'll just give you one more, because we don't have any non-commutative example here. Actually, there is a special case of this example studied in the notes. Functions that vanish on a parabola or something. Polynomial functions that vanish on a parabola. I would really want you to look at that carefully, because that's a very interesting example. And these kind of examples are sort of central in algebraic geometry. But maybe I'll write down one non-commutative example. So you let R be the ring of n by n matrices with real entries, let's say. Let I sub R, R is some number between 1 and n, be the matrices in this ring whose only non-zero entries are possibly in the rth column, whose only non-zero entries are in the rth column. So if n is 3, I1 looks like all matrices that look like this. All such matrices. I2 looks like all matrices that look like this. The first and the third column are 0. In the second column, you're allowed to have whatever you want. Verify that these are left ideals. Verify IR is a left ideal in M and R. And instead of real numbers, you can consider any commutative ring here, actually. At least any field, certainly. Similarly, you can write down right ideals. I'll leave you to guess what those are going to be. What about